In this video, we're going to calculate photon wavelengths from atomic energy transitions. We're given the Bohr model of the hydrogen atom, and an electron transitions from n equal to 3 to n equal to 2, emitting minus 1.89 eV of energy. We want to find A, what is the energy that the photon absorbs? B, what wavelength lambda of photon in units of nanometer is associated with the energy difference? C, what is the name series associated with the photon emitted/absorbed? Let's go look at the first part, the given. We're given the Bohr model of the hydrogen atom, which is shown below. So here we have a proton in the nucleus, which has a net positive 1 charge. Therefore, to make the atom electrically neutral, we must have an electron of negative 1 charge located outside the nucleus, either in the ground state n equal to 1, or the first excited state n equal to 2, or the second excited state n equal to 3. We're told that the electron is transitioning from n equal to 3 to n equal to 2. So as it's going downhill, it's going to emit energy, and it's going to emit minus 1.89 eV of energy. Keep in mind that anything that's bound in this direction is negative, meaning that it's bound. So the electron is bound. It's in an orbit going around the nucleus, then it's going to be bound, meaning that that direction is negative. Anything that's going in the opposite direction is positive. So let's say an electron were to move outwards and become free, well then it would have positive energy. So just keep that in mind, the orientation of negative versus positive for this atom. Now the electron has negative minus 1.89 eV of energy. So it's going to give off 1.89 of eV of energy, and we want to know what is the energy that the photon absorbs. So remember, negative means that it's bound inward. So since the photon is going to be taken away, so there's your photon. So here's the photon that's going to leave. Well, then the photon that leaves is going to be the opposite of the electron's energy. The exact opposite of the electron. So since the electron's energy that it is given off is a minus 1.89 eV, then the photon must gain 1.89 eV of energy. So a negative times a negative, negative 1 times negative 1 is just plus 1. And you can always check that out. You just can go to the Google calculator, put in negative 1, multiply negative 1, equals, you get plus 1. So we have plus 1 there, plus 1.89 eV. So the answer to the first question is 1.89 eV of energy that the photon gains. So we went ahead and put that in as our answer. Delta E is equal to 1.89 eV. Now what we want to find in part B is what wavelength of photon in nanometers is associated with this energy difference. So the wavelength is what we're searching for. So we need to find an equation, and these are our 3 equations that we want to use. Well, since we want to find wavelength, this first equation has no wavelength in it. The second and third do have wavelength in it. We are given delta E, and we want to solve for wavelength. H and C is a constant, so logically we would select number 2. Delta E is equal to HC over lambda. Well, we need to know some constants. We need to know H and C. So H is 6.63 times 10 to the minus 34th meter squared kilogram per second, and C is approximately equal to 3.00 times 10 to the 8th meters per second. So let's go multiply all of this and put it in. And I set up the equation already for us. Delta E is equal to HC over lambda, and we already know we have positive 1.89 of eV energy from the photon, and we want to convert out of eV. So we need a conversion. Here's our conversion. 1 eV is 1.6 times 10 to the minus 19th joules. So there it is. So that is equal to H, 6.63 times 10 to the minus 34th meters squared kilogram per second, multiplied by 3.00 times 10 to the 8th meters per second, divided by wavelength. So we want to solve. So first thing we want to do is multiply 6.63 times 10 to the minus 34th, multiply that by 3.00 times 10 to the 8th. So we clear that out, 6.63 EE minus 34, and we want to multiply that by 3.00 EE8 equal to 1.99 e to the minus 25. So we have 1.99 times e to the minus 25. I'm going to go ahead and put our wavelength on the bottom since we don't know it. Now we have this value that's up here. We need to divide by 1.6 times 10 to the minus 19. So let's go back to it. Divide by 1.6 e minus 19 equal to, we got our value. So we're dividing by this, and we have to also divide by positive 1.89. So now we want to divide by 1.89, and we're left with a value of 6.57, or about 6.58 times 10 to the minus 7th. So let's go put that in there, 6.58 times 10 to the minus 11th. And now we need to get our units. So I'll switch my pen color. So EV crosses out with EV on the left-hand side, and the only thing we're left with is a joule. And we only have the number 1. There's nothing else left. So we just put 1 joule there. We already multiplied everything else out. So we have a meter squared times a meter. That's a meter cubed. We have a second times a second. So that's divided by a second squared. And we have a kilogram up here. So our units are meter cubes, kilogram per second squared. So we want to now solve for wavelength. So we're going to multiply both sides of the equation by wavelength. And we want to divide both sides of the equation by 1 joule. So I'll put divide by 1 joule. And we want to divide by 1 joule on this side. So now we can cancel. Choose a different pen color. Make sure we got the right density of pen. Joule cancels with joule. We are left with, and 1 cancels with 1. So we're left with just the wavelength on the left-hand side. And wavelength crosses out on this right-hand side. So our units that are left over are going to be a meter cubed per kilogram, or meter cubed times kilogram, divided by second squared. And we're left with 6.58 times 10 to the minus 11th. And we have units of joules, but we want to get rid of our units of joules. And so 1 joule is 1 kilogram meter squared per kilogram squared. So we want to put this in here as well. So a joule's on the bottom, so we have a kilogram on the bottom. And then that is a meter squared next to it. And then we're going to divide that by a second squared. So I'll go back to my red pen. Our second squareds cancel out. Our kilograms cancel out. And our meter squared on the bottom cancels with the cubed at the top, leaving 1 meter. So we have our final answer of 6.58 times 10 to the minus 11th. But it asks for units of nanometers, and nanometers are 10 to the minus 9 meters. So we would need to move the decimal place 2 places to the right to give us 658 nanometers. And that is our final answer. We now have our wavelength. So I'll box my answer. So the C question is, what is the name series associated with the photon that is being emitted? In this case, we know that the photon's being emitted. So we have an answer of 658 nanometers. We're going from 3 to 2. We can take a look at the transitions, and we can see there's our 656 nanometers that we had calculated from an electron going from n equal to 3 to 2, and that's associated with our Balmer series.